Thanks again, everybody, for joining us, and thank you, Mary and Hans, for your time for this air-to-water heat pump webinar. Just a couple of housekeeping items. There will be a Q&A session after Hans's presentation. So any questions you might have, please put them in the Q&A box, not in the chat box. Feel free to throw anything else in the chat box, any remarks or thoughts you might have. We will be recording this, and anybody who registered for the webinar, even if they're not here right now, will get a link to the recording, the slides, as well as some other information from us. And with that, I will hand it over to Mary to introduce Hans.
Thank you. Welcome, everybody. Welcome, Hans. Hans is sitting in Boulder, and he told me, unfortunately, they didn't get any of this lovely rain that at least some of us on the Western Slope did get. So thank you for being with us. It's great that with Zoom, you can be sitting anywhere and listen to such a great presentation. So Hans started a company called BrightSense that provides solutions for switching to all electric buildings. So retrofitting existing homes and buildings to allow like net zero and net positive energy. We're hearing these terms so much more now. They develop innovative mechanical systems, which they are really innovative now, using air source and geothermal heat pumps that are right sized for the demands, because a lot of times the old boiler systems were so oversized, but now it's really important to right size these heat pumps, right, Hans? So exactly. They actually really help get you the best performance heat pump for your home or business. And then it provides much more comfort and a healthy indoor environment for you at the best efficiency. So Hans, we're so glad to have you with us again, and take it away.
Awesome. Thank you, Mary. I appreciate that. Appreciate the opportunity, and thanks everyone. Good afternoon. Thanks for joining us. Yeah, so today we are talking about hydronic air source, low temperature or cold climate heat pumps. Those are very big words. Let's take a look at what they actually mean. So hydronic means water based. So we are heating water primarily, in heating. We can also chill the water. We'll be talking about that later. Air source means that our heat pump sits outside and it absorbs the thermal energy from the ambient air. Low temperature or cold climate means that they are designed for our heating dominated frigid climates, with temperatures sometimes below 0 degrees Fahrenheit. For radiant, radiant heat is the most comfortable type of distribution in our homes. It works really well with heat pumps because it's low temperature heat. So that's why we put that in the title as well. I need to figure out how I can switch to the next slide. We don't need to spend much time here on this slide. Mary provided a really lovely introduction. I've always had a passion for energy efficiency, and I'm really glad and very fortunate that I can use that to make my living. We work with architects, builders and developers, and homeowners, obviously helping make homes more efficient, and helping in the transition to all electric homes away from gas. Homes are a complex system, and it's really important that if you make changes to a home, that you consider all the different components, because when you change one, it can affect everything else. So walls, foundation, slab and windows, yeah, the so-called envelope. Yeah, it's very important to have a system that works really well. It doesn't make sense to have really super insulated walls and then crappy windows, for instance. All equipment like kitchen appliances, they all need to be considered when we are sizing and developing the heating and sometimes cooling equipment for a home. What types of space conditioning equipment is there? Well, there's the traditional boiler that, yeah, boilers heat water. Then there are furnaces. Furnaces heat air. Those are, yeah, the boilers are most prominent in our Rocky Mountain climate because, yeah, we have it's a heating dominated climate. Furnaces are very often combined with air conditioners, and we'll be talking about that in a little bit. Then there are wood stoves, and then there's electric resistance heat, yes, electric baseboard, and there is the electric resistance mats that some people have under their bathroom tile, for instance. And then, yeah, the fifth and what we will be talking about today is our heat pumps. What types of heat pumps are there? Yeah, a lot of people are familiar with the typical window air conditioner, but you may not know that your fridge is actually a heat pump. It pumps heat from inside the cabinet into the kitchen, and yeah, when you remove the heat from inside the cabinet, temperature drops. That's what we want in the fridge or the freezer. But that heat has to be pumped somewhere. That's why the fridge is warm at the back. The opposite of the fridge, if you will, is the heat pump hot water heater. Those have been gaining a lot of ground in recent years, and they've become really efficient, and the prices have dropped, so they've become really popular. So what they do, they pick up heat from the surrounding air in the utility room, typically where those are installed, and they pump that heat and inside the tank where it heats the water. So you know, they're very efficient water heaters. And then yeah, there are the regular air conditioners and the heating and cooling heat pumps that we will be talking about today. Mini split heat pumps are one of them, and then the hydronic heat pumps. How does a heat pump work? Yeah, we just said that the heat pump pumps heat from one side to another. So on one side, it's absorbed, and that's where the refrigerant, the refrigeration fluid evaporates. Yeah, the evaporation process requires energy, and so that helps absorb thermal energy. That is then transported with the fluid as the fluid continues down the internal piping, so that thermal energy is continues, is pumped around by the compressor. There are a few things that happen. It's compressed and it's pushed over to the condenser, where during condensation the heat is rejected, and that's where the heat is usable if we want to heat the building, for instance. because the process is reversible, we can also absorb thermal energy in the home, and which leads to a cooling effect, and then that heat is pumped outside, where we're shedding it, getting rid of that heat. How about efficiency? What does that look like? There's the coefficient of performance. What does that mean? So in this example here, we are absorbing 3 units of energy at the evaporator. This heat pump that we are looking at here, that uses 1 unit of energy to operate the compressor. And then we have 3 plus 1, we have 4 units of energy at the condenser. So that's the usable thermal energy that heats our house. So in this example, the 4 versus 1, that's a coefficient of performance of 4. We're paying for 1 unit of energy for operating the heat pump. We get 3 units for free, a total of 4. So that's a coefficient of performance of 4, or 400% efficiency. If we were to be cooling, the effective cooling energy is 3. So 3 versus 1 would be a coefficient of performance of 3, or 300% in cooling. So the typical efficiencies of heat pumps are somewhere between 200 and 500%. On a milder day, an air source heat pump is more efficient. On a colder day, it's less efficient. What does an air source heat pump look like? What does a typical installation look like? So this is a photo of an actual installation. The heat pump sits on what we call a snow stand. To elevate it, we don't want it to get buried in a snowdrift. So that's why it's elevated about 2 feet. Then we have the piping that connects into the house, into our mechanical room, utility room. And so the heat pump, it needs some clearance, because we want airflow to be unobstructed. We want a lot of air to move around the heat pump, because our thermal energy that we are looking to harvest, that is comes loaded onto the air. And so we don't want to have any fencing or a shrubbery that reduces our airflow. We want about 12 inches clearance behind it. Installing the heat pump against ideally a south-facing or east or west-facing wall that is a little warmer, from the sun, is beneficial. North-facing walls in our climate are not ideal. The snow and ice don't melt sometimes until July. So we're trying to avoid an installation against a north-facing wall. Operating range, very important. Today's air source heat pumps operate down below 0 degrees, -15, -25 degrees. There are some models available that operate when it's that cold. Certainly, the output and efficiency are lower because there's less thermal energy to harvest when it's colder. And they can produce 125 degrees water in heating. when we're cooling, we can produce 40-degree water. Hydronic heat pumps can be combined with many different distribution systems. Ideal is always radiant. There's the in-floor radiant, either in slab or a product like warm board, eco-warm panels. Staple up works under certain circumstances. Or cast iron, European style panel radiators and towel warmers are also really good in combination with a heat pump. Heat pumps are not compatible with hot water baseboard because hot water baseboard requires really hot water, as is in the name. 160, 180 degrees are needed for hot water baseboard to have some decent output. At this point, there is no heat pump available that can produce water this warm, this hot. A couple more words regarding about warm board. These are plywood panels with grooves installed from the factory that are mostly used in new construction. EcoWarm is a similar product. So these work really well on elevated floors. If you have on the above a basement or above a crawl space. This large picture here shows radiant piping that is stapled down on a subfloor just before a concrete slab is poured. So these will be embedded in a few inches of concrete or gypcrete. That concrete or gypcrete certainly provides thermal mass. That helps the home coast through those large temperature swings that we see here in Colorado between day and night. Sometimes 40 degrees in the morning and 85 degrees in the afternoon. And so when you have a house with a really good thermal mass, you will be coasting right through those temperature swings, and you won't notice any of that. Just a couple of words about staple up. The bottom left picture shows staple up, looking up between the floor joists. There is a product called a joist track. These are aluminum profiles that the radiant piping snaps into. Those spread out the heat and provide a really good heat transfer. Nevertheless, a staple up has a lower output than the in-floor radiant. So you do need to have a really well insulated home for staple up to work, because the heat has to travel through the complete floor assembly from the bottom to the top before it reaches the room. And so it requires, as I said, it requires a well-insulated home for that to work properly. For just a few words in regards to cooling. So there is certainly the option of doing radiant cooling. So you're using your existing radiant floor infrastructure, and you pump chilled water through those pipes, but it's a little tricky. It requires a certain infrastructure, a humidity sensor, because we don't want to have condensation anywhere on the floor, and it's also very slow. yeah, it might work really well here on the Front Range, where we see over 100 degrees and we have many hours of cooling in a day. But when you're up at altitude in a mountain town, and you might only need cooling for a few hours in the late afternoon, it would be too slow. Yeah, you would have to turn it on in advance, several hours in advance. So that's not ideal. So a fan coil is much faster to respond. Here are a few examples. Yeah, so these are hydronic fan coils. Some of them look like a mini split. And they work in a similar fashion. Yeah, they can be used with hot water or with chilled water. Yeah, there are mini split looking ones like these high wall. Then there's these consoles. These are slim wall or can be ceiling mounted. And then there's these guys here. These are it's basically just the internals, and they can be built into a wall cavity, so they can be concealed and somewhat hidden. Yeah, all of those are point sources, so you would need one for each room that needs cooling. So yeah, so I see that quite a bit in mountain communities, that there may be only a couple of rooms that might need cooling. Yeah, maybe a few bedrooms, south-facing bedrooms, and maybe the great room, living room, and so those can be installed in those particular rooms, and yeah, you'd be all set. For homes that have a larger cooling load, there are unitary air handlers. So these basically, they work with whole house ductwork, full-size sheet metal ductwork, and also they accept hot and chilled water, and work in a similar fashion. But yeah, just as a side note, the preferred way of heating is certainly the in-floor radiant, because it's so much more comfortable, without draft, without noise, and without requiring ductwork. How about some heat pump performance? Let's talk about heat pump performance. This chart, it shows the outdoor temperature at the bottom, from -20 degrees to 80 degrees. The orange curve here, this one, recently I realized that there are two orange curves, but the dark orange, this is the heating load of our home. This is a sample home that has a heating load of 36,000 BTUs per hour at -5 degrees Fahrenheit. So here's -5 degrees, the red dot, 36,000 BTUs. At 60 degrees, our heating load is 0. We don't need to heat the house when it's 60 degrees outside and sunny. So the colder it gets, the greater the heating load. These three other curves are three heat pump sizes. This is a 36,000 BTU heat pump, 50,000 BTU heat pump, and a 60,000 BTU heat pump. These are nominal outputs. They're typically measured at 47 degrees. That's an industry standard. The reason why these are not at, this one here, not at 36, at 47 degrees. 47 degrees is over here, but this one is lower than 36. It should be up here normally, but the nominal output is measured at sea level. So we here at altitude, we have thinner air, And so we have a thin air penalty. That's why these are so-called derated. That's why these curves are lower than the nominal output. We take that into consideration automatically when we are sizing systems, heat pumps for systems here, because that's important. We don't want to leave people in the cold. I got the question last time. This heating load. What does that represent? What type of a house? I would say, if you have a 2,000 square foot home that's 20-year-old, hasn't been upgraded, so still the original windows and so forth. In a town like Carbondale, I would expect that your house has roughly 36,000 BTU load at -5 degrees. If it's a new home that was built recently to code, basically code minimum, then I would expect a 3,000 square foot home would have this kind of a load. If you have a passive house, then a passive house of 4,000 square feet or larger, I would also expect to have a load of no more than 36. Let's dive into this here a little more, and let's select the 60,000 BTU heat pump. So this is the curve, the output curve, you will notice that the heat pump output, it's lower the colder it is, which totally makes sense, because there's less BTUs to harvest in colder outside air. That's really unfortunate, because our heating load is exactly the opposite. It's greater the colder it is. But unfortunately, that's the case, and that's physics, and we should not try to beat physics. Otherwise, we'd be left in the cold. So where those two curves meet, the home load and the heat pump output, marked here with the purple dot, that is our so-called balance point. So in this example here, we have a balance point of 0 degrees. That means the heat pump has enough output to heat this home down to 0 degrees. It has enough capacity, but temperatures below 0 degrees, the heat pump will need some help. Otherwise, the temperature in this particular home would be dropping whenever temperatures drop below 0 degrees. This chart here shows the energy. So down to the balance point, the beige area, that's the energy that the heat pump provides by itself. When temperatures drop below the balance point, it will still produce this energy that is marked in blue. But the green, that's the supplemental energy that we need to have a second heat source that provides this amount of energy to prevent any reduction in comfort. At one point, our heat pump might say, sorry, it's so cold, there's really no BTUs in our outside air because it's -20 degrees. I need more help, and that's when our if we are in a climate that has temperatures below -20 degrees, then we do need a backup that can cover 100% of our load, and so that's the yellow shaded area here indicates this energy. Now Another fancy chart. What does that mean? Let's talk about the weather. Yeah, so how often are we experiencing temperatures, yeah, where the heat pump might be struggling? This here is a so-called temperature bin hour data. It again has the outdoor temperature at the bottom, yeah, negative 30 degrees up to 100 degrees. And those columns, those indicate the hours in a year at those temperatures. So yeah, if we look at this temperature interval between 25 and 30 degrees, yeah, there's roughly 800 hours in a year at, yeah, this is Aspen airport data, roughly 800 hours between 25 and 30 degrees in total in a year. So this is really important data because this tells us how many hours below zero are there and how many hours below negative 20 degrees when we might need 100% backup. So we are always developing this this temperature chart for the locations where we are sizing heat pumps for. And that tells us what our efficiency is going to be and what size backup we need, if any. It also tells us if we need any cooling. Now, of course, this is historic data. So from the last 10 years, it doesn't tell us how the future is going to look, but yeah, certainly we are hoping by installing heat pumps and reducing our carbon emissions, the planet will not be continuing to warm as it has in recent years. So when we put these two charts together, this is what I was just mentioning. In this example, the simulation tells us that we would have roughly 72 hours in a heating season that would need supplemental heat. In this example, and we would have about 2 hours of 100% backup heat. So in this situation, if we use this large 60,000 BTU heat pump for this 36,000 BTU home, we would need a backup heater that can do provide 100% for these 2 hours. If we look at the total energy that is provided to the home over the course of a whole heating season, we can expect that the heat pump itself provides 99% of that heating energy, and only 1% is provided by this backup boiler. So even if this backup boiler, we're using an electric boiler, for instance, that is only 100% efficient. That really doesn't matter because 12,000 kilowatt hours consumed by the heat pump and only 420 consumed by the supplemental backup boiler. That really does not play a big role. It wouldn't make sense to install 2 heat pumps in this case. The little electric boiler is a lot cheaper than a second heat pump, and if that is only used for a few hours here and there, really the second heat pump would not be a good investment. In particular because we would still need 100% backup for those few hours where the heat pumps might be struggling. What we can also develop in most situations is tell people what their rough energy bills are going to be, and if they are interested in achieving net zero energy or net positive energy, what size photovoltaic system they would need to achieve that. these numbers are always, you need to take those with a grain of salt, because similar to driving a car, you can also operate a home very efficiently, but also less efficient. You can drive a car very frugally and achieve a very high gas mileage, or you can floor it and have to stop at every second gas station. That's the same with a home. So these are estimations that very much depend on operator performance. What does a typical hydronic heat pump system look like? So this is a very simple heating only system. If you are familiar with a typical boiler system, this will look very, very familiar. The distribution side here, where our radiant zones are, the thermostat, the zone panel, this is very much identical to a typical boiler system. The only difference there is really is the heat pump that sits outside instead of the boiler in the mechanical room, the utility room, and the buffer tank. This buffer tank we are using for two purposes, for two reasons. One is the heat pump wants to see a constant flow rate, a fluid flow rate, where on the radiant side you could have one zone calling, or you could have 5 zones calling. So the flow rate on the system side here varies greatly. The heat pump wouldn't like that. That's why we have this buffer tank as a so-called hydraulic separator. And the other reason is sometimes the heat pump has to do defrosting. And so it would be out of commission for a few minutes, and during those 5 minutes of defrosting, there still is thermal energy stored in the buffer tank, and so there would be no interruption to our heat delivery to the home. Here's another piping diagram. Here we just added the fan coils. So those can be used for supplemental heating or cooling. They're piped slightly differently. Sometimes it doesn't make sense to install radiant in a certain part of the home. It would be too expensive. So a fan coil can certainly also be used for heating. In a loft area, for instance, a fan coil might make sense. As warm air rises, the loft may be warmer and have a very small heating load. So a fan coil might be a cheaper option for that. So we system design is very flexible, and we have many different options to customize. This type of system, if this home were to require cooling, this system would have a seasonal switch over. That means sometimes in the spring, we would switch it from winter to summer mode. And then when there is a demand from a thermostat, I would provide cooling in summer mode. And then in the fall, we would be switching it back to heating mode. And then, so during cooling mode, obviously the tank would be chilled, water in the tank. In heating mode, the water in the tank would get heated. This manual seasonal switchover, it prevents that we are chilling down a hot tank, or we are heating up a chilled tank. We have these large temperature swings here in Colorado, And yeah, so if you were to automate that without a manual intervention, yeah, it could happen that when it's 40 degrees in the morning, yeah, the tank would get heated. And then in the afternoon, when you've got 80 degrees, it might get chilled. So that, yeah, during shoulder seasons, that would not be efficient. Yeah, you might not even need any heating or cooling in that home. But still, yeah, the controller would call for heating in the morning and cooling in the afternoon. And so the manual switchover prevents that from happening, from wasting any energy.
Hey, Hans, sorry to interrupt. Just wanted to give you a time check where it's about 5:40, just after 5:40. So want to give a few minutes for the Q&A at the end. So we wrap this up.
Sounds good. Appreciate it. Thank you.
Minutes.
Yeah. Just quickly, so this is a more sophisticated system. This uses two tanks, so a hot tank and a cold tank. That is certainly an option as well for situations where yeah, we might need cooling in the afternoon and heating in the morning, or we might need yeah, heating on the north side of the house and cooling on the south side of the house. So this is certainly an option as well. Yeah, where the hot tank would typically have priority, and then we have a chill tank, so we would not risk yeah, heating or chilling down water that was previously heated or cooled. I get the question a lot. Yeah, can we also make our domestic hot water with a hydronic heat pump? And yeah, the simple answer is yes, you can. However, yeah, in well-insulated homes, the domestic hot water load is often greater than the space heating load, and so that would yeah, in most situations require two heat pumps then. So you have hot water on a really cold day. It also makes the system really complicated. Yeah, you have a hot tank with a coil, and then you need a domestic hot water tank. And if you want to have cooling as well, then you need a third cooling tank. So this quickly makes your mechanical room look like a submarine. It gets very expensive. It's not cost effective, really. Yeah, what's more cost effective is using standalone heat pump domestic hot water heater for your domestic, and yeah, basically separating your hot water from your space heating system. If you have a higher load, heat pumps can certainly be cascaded. Yeah, 2, 3, 4 heat pumps is absolutely no problem, and works just the same as you would yeah, cascade boilers. Yeah, those would be staged and operation a runtime. Yeah, making sure they all get the same runtime and so forth. Controllers are available, yeah, that do the staging. How about operating cost of a heat pump compared to a gas system? Natural gas prices have increased recently, yeah, or this year, and so this is calculation is based on some recent data. When we compare the price of natural gas using an 85% efficient gas boiler, and comparing that with yeah, electricity, we would need a heat pump with a coefficient of performance of 3 in order to achieve our heat generation at the same price as natural gas at the moment. coefficient of performance of 3 is achievable in our climate with an air source heat pump. So the annual average of a COP of 3 is realistic. So right now, with the current natural gas prices, you can expect that your heating bill is not going to increase significantly over a natural gas fired boiler. If you generate your own electricity with a local PV system, your electricity cost is lower, and then your operating cost with a heat pump would certainly be lower than a natural gas boiler. How about propane? Propane has risen to $3 a gallon last winter. That makes propane really expensive, and a heat pump with a coefficient of performance of 0.9 is already giving you the same cost. So 0.9, 1 would be the efficiency of electric resistance heat. So basically electric baseboard. So even you can basically with electric baseboard, you would already be saving money over propane at $3 a gallon. So with a heat pump and a coefficient of performance of 3, you would be producing heat at 1/3 the cost of a gas fired boiler. If you have your own PV system, your cost would be even lower than that. How about the carbon emissions? I just looked up this morning, the latest carbon data for the electric grid in Colorado that's available is from 2020. So when we compare the carbon emissions to produce 1 kilowatt-hour of electricity here in Colorado, and compare that to the carbon emissions of natural gas or propane, we would need a heat pump with a coefficient of performance of 2.7, or with natural gas, or 2.2 with propane, to reach equal carbon emissions than those gas-fired appliances. Again, based on an 85% efficient natural gas or propane-fired boiler. If we go back and our heat pump operates at a coefficient of performance of 3, that means our carbon emissions are already today lower than those of the gas-fired appliance. If we again produce our own renewable energy using our own PV system, our carbon emissions would be even lower than that. I should point out that Holy Cross is already at 50% renewable energy today, so quite a bit better than the average electricity across Colorado, the rest of Colorado. So if you get your electricity from Holy Cross, you already have an advantage with a heat pump today, an even greater advantage. Winding down, just a quick summary. Air source heat pumps are an established technology. They are modern, they're very efficient, quiet, and cost effective. Lower carbon emissions, we saw just in the last slide. A lot of R&D is being put into, R&D money is put into heat pump technology. We are at the beginning of the heat pump era. So new refrigerants are being developed that are more climate friendly. Heat pumps are low maintenance, require very little maintenance. If you want to go all electric without loss of comfort, an air source heat pump is a good choice. You're not taking any risk. It would be very difficult to achieve net zero or net positive energy without a heat pump. So I like to say that they're required. And the same, they are required for carbon neutral or low carbon emissions home. That concludes my presentation. Thank you so much. Here's my contact information. We are the reps for Arctic hydronic heat pumps.
Thank you.
So I'll hand it over to Mary and Diego for the question and answers.
Thank you, Hans.
Thanks, Hans.
Well, thanks everybody. Thanks again, Hans, for that great presentation. As you can see on this slide, there are various rebates available for the installation of heat pump systems. So again, we'll be sending out these slides, and if you live in the Vail Valley, Walking Mountains and Energy Smart Colorado have a rebate for you. In the Roaring Fork Valley, that will go through CORE. Holy Cross Energy also has significant rebates available for heat pump projects. So if you are looking into installing one, feel free to reach out to myself or to Mary, and we can get you connected with what's available in your area.
Right. And you can take both the utility and some of the local nonprofit heat pump rebates. And also the Inflation Reduction Act, which we all call IRA now, is going to have some tax credit rebates coming up next year. So we're all trying to learn more about that too. So there'll be some other help from the federal IRA.
And the state of Colorado also recently passed some legislation exempting heat pumps and other decarbonizing building materials from sales tax. And there's also a state tax credit available for the installation of heat pump systems. And that's from the state of Colorado. So going into that, we've got a few questions here in the Q&A. We'll start right at the top from Laura. Can air to water heat pumps be installed in a large crawl space?
So the heat pump itself has to be installed outside. If you were to install it in a garage or in any enclosed space, you would basically create a freezer, because it would absorb all that thermal energy from that room, and it would freeze down that room, at one point the heat pump would stop operating because there's no thermal energy left to operate. So no, that would not work. It has to be outside, with ample airflow around it. I mentioned before, we want to have some clearance. I understand that some HOAs, they require that there's some fencing or something, and shrubbery installed around a heat pump so you don't see it from the street, and that can certainly be done. That's no problem, but the heat pump needs to sit outside.
Thanks, Hans.
Thanks.
Got another question here. Sorry, go ahead, Mary.
Let's do Rachel. I'll go. Rachel's asking, and this is a great question. I don't even know this answer. Is there any off-grid heat pumps available in direct current for PV and battery remote locations? So this is somebody that isn't on a utility, and that's a really great question. I don't know.
I'm not aware that there are any DC heat pumps. Yeah, a lot of heat pumps today, they use DC compressors because the other DC motor is so much more efficient and it's variable speed. But yeah, they have inverters built in, so they rely on 240 volt AC. I certainly get the question a lot. Off-grid cabins, yeah, sometimes it would be exorbitantly expensive to bring power to a remote property, but it's you would need a lot of batteries, yeah, to unless it's a really small cabin, a small, very well insulated cabin. I would say it would not be cost effective to try to do heat pumps with off-grid at this point. Yeah, batteries are still too expensive. And the other few projects where we did the calculation, yeah, the upfront cost for all the infrastructure would have been so expensive, yeah, that it really did not make sense.
Great.
And you do not want to have a propane generator generating your electricity so you can run a heat pump. Yeah, that would not make sense, because a propane generator generates the kilowatt hour at about $1. Yeah, $3 a gallon for propane, and then yeah, that
okay, yeah,
is not efficient either.
right, yeah, and that's the whole point, is going all electric with these heat pumps. So that makes total sense. So Alyssa is asking, what makes hydronic systems more energy efficient than conventional boilers and air-to-air heating systems?
So an air-to-air heat pump is very similar. Yeah, only that the hydronic heat pump heats and chills water, where air-to-air systems, they heat and chill air. So yeah, we are sharing a lot of the same components, and our efficiency is also very similar. Yeah, the problem of the air-to-air heat pump at altitude is that you have the outdoor unit that's derated, yeah, from the thin air, and you have your indoor unit also derated. So you can easily have a 20% reduction in output because of that double derate, where the hydronic heat pump, only the outdoor unit is derated. You know, your water that's in your radiant piping, that's pressurized, it doesn't care that the air is thinner. So yeah, the output and efficiency at altitude is significantly less. Yeah, the reduction is smaller in a hydronic system. The heat pump, as we talked about, it pumps thermal energy from one place to another. Yeah, so that's why the heat pump is called a renewable energy source. It comes up with the thermal energy that heats your house from the outside. It does not have to be generated by burning fuel, and that's what makes the heat pump yeah, more efficient than a boiler.
Great. Kevin is asking if we want to replace a gas boiler that serves both radiant floors and hot water baseboards, and we see that a lot in our territory. Is there an efficient way to boost the temperature to provide the temperature needed for the baseboard?
So the short answer is no. There is no good way to boost hot water baseboard. People have certainly tried it. Yeah, you can add more baseboard length, linear feet. Some people have tried doubling up the fin tubes, yeah, one on top of the other. But your hot water baseboard output goes down to maybe 10% if you supply 120-degree water through it. So it's really not providing much. So yeah, it really depends what part of your house, what portion, percentage of your house has the hot water baseboard. Can you maybe retrofit, staple up in that area? Can you maybe do a fan coil? You could try converting to European panel radiators. But you would have to redo your piping also, because the panel radiators, they want home run piping to each one directly, where the baseboard is all in series. So it would require quite a bit of probably drywall work to, depending what your access is from underneath. So there's no easy fix.
Yeah.
Thanks, Hans. Melissa's also asking, what changes do you make to the system to make it work conversely for cooling instead of heating? Is it difficult to switch the mode of the system? And Alyssa, I believe he did cover this in one of his slides. Hans, I don't know if you want to
Using
give
the
a
fan
really quick
coils, right?
explanation.
So down in the deep south, or even the Midwest, where cooling involves a lot of humidity removal because it's just so humid. The humidity removal can actually be greater. The energy required for humidity removal can actually be greater than the actual temperature reduction. So you need to have a system that is capable of removing humidity from the air, and that requires a forced air system. So either a fan coil, or a ducted or a ductless fan coil system. But it certainly works with a hydronic heat pump. I mean, if you don't have a radiant component, at least, then it wouldn't make sense to do a hydronic system. Then you should go straight to an air-to-air system. It wouldn't make sense to heat and chill water in a buffer tank and then convert it back to hot or chilled air if you don't have a radiant system.
Right.
That would add cost that does not give you any efficiency advantages. So you do want to have some radiant in order to for the hydronic heat pump to make sense.
And we have done workshops with people with the hydronic systems, baseboard gas systems, with the mini split, like the air source mini split heat pump, which was it's a ductless system. So another option. So Rachel's asking, will a lock sidearm, which is the name of a boiler brand, sidearm, perform the same function as the Arctic buffer tank?
So the sidearm is the domestic hot water heater. So the Arctic heat pump can certainly also make you a domestic hot water, but it's not cost effective to do that with a heat pump. I would recommend having the other standalone heat pump hot water heater for your domestic. Basically replace that sidearm buffer tank with the standalone heat pump hot water heater, and separate the space heating from the domestic hot water heater. And that's from a cost standpoint, it does not make financial sense to buy a specialty tank with a domestic hot water coil, and those tanks have gotten very expensive. It's not cost effective.
Great. Thanks. Alyssa's got another question. How well can this technology be utilized in tropical climates or countries where space heating is not needed as much? How much does this system contribute to energy saving and energy recovery in tropical climates? And Alyssa, I can let you know right now, in terms of in-floor radiant heating, obviously that's not really going to be prevalent there. And so air-to-water system might not be the best, but air-to-air heat pumps definitely still provide that super high efficiency for cooling. as well as for heating.
Yes.
So
Exactly, yes.
Right. And then Hans, somebody, and this is a great question, is what's the cost? Let's say I have a 3,000 square foot home with a boiler system. What would be an estimated cost? And we can help you a little bit in our territory because the cost of living is pretty high. What are you seeing as a cost to replace an existing boiler system with this heat pump system?
So if we're assuming that one of the large heat pumps is sufficient, you can expect to pay about $10,000 for the engine part. So the heat pump, the buffer tank, and heat pump controller. Yeah, if your existing gas boiler still has some life in it, and you don't want to get rid of your gas pipe altogether, you can certainly keep your existing gas boiler for the backup that we talked about. And yeah, if it's at the end of its life, replacing it with an electric boiler, yeah, that's roughly maybe another $2,000. But so, yeah, so and that's material only. Yeah, labor, installation labor is on top of that. And that's really difficult to answer, yeah, what it would cost. It really depends on the circumstances. Yeah, how easily is it accessible, and so forth. How much of the piping needs to be redone. So yeah, that I really don't want to
Right.
make a guess. Yeah.
Yeah. So I'll make a guess for you just because I know people. So it's not unusual to see between $25,000 and $30,000 for heat pump systems, especially the mini splits that go into drywall, stuff like that. And a lot of it is because the cost of living and the labor cost here. So it's not so much the cost of equipment, although that's kind of gone up during the pandemic also, but the labor costs have gone up. So that's why, you can get up to, if you're converting from gas or propane, you can get up to $4,000 from Holy Cross, and then potentially another $3,500 from Walking Mountains or from Core. There's also some really good rebates. So depending on what county you're in, when you look at the cost of replacing your gas or propane boiler and adding central air conditioning, the rebates kind of bridge that incremental gap and help lessen that cost.
And then potentially, yeah, Colorado income tax rebates, and also the
right. IRA.
The Inflation Reduction Act, which goes into effect January 1st. Yeah.
Yeah, and we're still learning about that. So if you guys use tax preparers, you want to talk to your tax preparer. They might have their finger on what's really going on. That money, for the federal money, my understanding is it's going to flow to the state, and the state will then distribute it. So it's going to be a few months before we all understand. But that's great that we are going to have some more incentives. Cameron asks, does the tariff on Canada still impact the equipment cost?
So the tariff is actually not Canada. It's because the Arctic heat pumps are assembled in China, and that's the China tariff. It doesn't matter that the equipment comes across the border from Canada. It's where it was manufactured, and so that's a 25% tax that was introduced during the last administration, and the Biden administration kept that in place for now. I know they talked about it, but it's still in place for now, and that's where that money goes. That goes to the government.
Thanks.
That's great. Right.
And then just a final couple of questions here. And these questions might be better asked towards a contractor. But I've got an 800 square feet of floor for radiant heat. what product is the best and most economical, and then I have more than 2,000 square feet and 2 levels, I assume total. What air conditioner is good and cheap to buy and install?
So regarding the radiant, yeah, so the products that I mentioned in the presentation, the warm board and the eco-warm, that requires ripping up the existing floor surfaces, and because that is installed in instead of the subfloor, and so that requires a major renovation. It brings the floor up, so those products are mostly used in new construction. So for retrofitting a radiant floor in an existing home, staple up is typically what is being used if you have access to the subfloor from underneath, from a crawl space or from a basement that is not finished. If the basement is finished, you would have to rip down the drywall, ceiling, so it's more involved. If you wanted to retrofit European style panel radiators, you would also need to have access from underneath for the piping, because the piping connects from the below. Retrofitting radiant is typically requires a larger renovation. In new construction, it is certainly not a big deal. The architect would plan around it, and it does not add a lot of cost in terms of infrastructure.
Thanks.
Regarding to the air conditioning, for the 2,000 square feet, it certainly depends. How many rooms you have. If it's just a few rooms, then you may want to just install a few fan coils here and there. If it's just air conditioning, if you have a functioning separate heating system, then you want to look at a mini split type system.
Right.
If you have more rooms on multiple floors, retrofitting air conditioning, basically a whole ducted system, that also requires a major renovation. It might not make sense to do that, financial sense.
Right.
Great, thanks.
And we have one really great last question, right, John? Glad you asked this. So we have a lot of snow melt in our territory. So how do you do snow melt with a heat pump? Do we have to wait for some technology?
No, the heat pumps are certainly capable of you can do a snow melt with 120-degree water, but the phase change from the snow to liquid, it requires a lot of energy. It requires a lot of horsepower. That's why snow melt boilers are typically large, very large.
Yes.
So our largest heat pump, the 60,000, it has capacity for 300 square feet of snow melt, and that's exclusively doing snow melt, no space heating in the home. If you were to use it exclusively for snow melt, so 300 square feet, that's basically the apron in front of your garage. It's not much.
Right.
So you would be paying quite a bit of money. Snow melt system is expensive. Not so much to operate it, but the installation, the equipment and installation. So it requires quite an investment, and I mean, to $10,000 for an equipment, and that's the heat pump only,
right?
For 300 square feet. One could argue that you can hire a lot of teenagers to shovel for $10,000.
Yeah. That there is that option, but a lot of times here it isn't such an option. So
it's
but
not
that's
an
great.
option, yes.
Yeah, so that's great. It is something we're waiting for, some heat pumps to kind of get a little bigger, be able to handle these bigger loads, especially in commercial buildings. So
Yep.
we're not quite there yet, but I'm hoping technology is coming down the
A lot of
pipeline.
money is being invested in this technology. We're right at the beginning of this big heat pump era,
Mhm.
I want to call it, and so yeah, I'm really excited and curious to see what's coming. We already have really good product today that meets a lot of our needs, but yeah, we need high temperature heat pumps, and yeah, more climate friendly refrigerants and things like that. But yeah, we will be getting there in the near future.
Thank you. Great.
Great. Well, thanks again, Hans, for your time and for this great presentation. Thanks, Mary, as well, for helping facilitate. Just as a reminder, we will be sending the recording and slides out, should be early next week. So just be on the lookout for that. And if anybody has any other questions about rebates or heat pump systems, feel free to contact us here at Walking Mountains or Mary at Holy Cross Energy. We'll provide all that contact information from these slides in that follow-up. So thanks again.
Jagger, sorry, Jagger, there's one question. I don't know the answer. Are we giving people a certificate of participation for this webinar? If people need like AIA, architect kind of, is there any?
No,
Okay.
we don't have a certificate of participation. This is not a continuing education accredited webinar. It's more informational for the general public. So
Great. Super.
Okay.
All right, you guys have a great evening, and hopefully the leaves are going to change soon.
Yeah. Thanks, everybody.
All right. Thank you
Yep.
for your time.
Okay. Thank you for